Sir, good morning, sir. Let me start the session, sir.
Hello.
Sir, let me start the session, sir.
Okay, sir. Okay, sure.
Okay, sir. Very good morning to all gathered here. I'd like to welcome all the participants for a day 6 session 1 of AICTE sponsor 2 weeks online faculty development program on emerging trends and challenges in a VLSI mixed signal processing for a fourth industrial revolution. Welcome you all. It's my pleasure to welcome our today's resource person, Mr. Navin Shankar, Field Application Engineer, Untitled Technologies, Bangalore, who is going to hand over the session in the topic of design of SER-based data converter using a Cadence EDA tool. Welcome you, sir. Sunshine is a welcome thing. It brings a lot of brightness. In this way, I would like to give a short intro about our resource person. He completed his Bachelor of Engineering in Electrical, Electronics and Communication Engineering at Srinivasa Institute of Engineering and Technology at 2010 and completed his Master of Engineering in Applied Electronics at Valamore Engineering College at 2013. Mr. Navin Shankar is working as a field application engineer at Entable Technologies, Bangalore since 2017. His roles include logical and physical synthesis, PNR flow consisting of various steps such as floor pan, power pan, sanity check, placement, clock tree synthesis, routing, and design optimization. He is having an experience of 2 years in the field of application engineer for EDA products. He has supported on some of the design-related queries at DI event levels like OTL design, OTL synthesis, physical design, physical verification in a PD flow. He is also trained in a ASIC physical design and custom IC designs with hands-on experiences in a back-end design flow, including like synthesis, flow planning, power planning, placement, clock tree synthesis, routing, static timing analysis like OCV, CPPR, multi-cycle part, and physical verifications like DRC and LVS. In this way, I would like to hand over the session to our today's resource person, Mr. Navin Shankar. Please, sir.
Can I share my screen, sir?
Yes, sir. You can share now, sir. Just a minute, sir.
You'll have to stop sharing.
Yes. You can share now, sir.
Yeah, thank you. Good morning, all. This is Naveen Shankar, application engineer for Cadence from Interpol Technologies Private Limited, Bangalore. First of all, I would like to thank the management of Kongunadu College of Engineering and Technology for this wonderful opportunity in order to handhold all the participants on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. And today's topic that we are going to discuss is about successive approximation based analog to digital converter. Okay, so before we start, let me take you through the agenda for today's session. Okay, and uh, I'd like to give some information about myself and about the company. Uh, I have an overall experience of over 6 years. Okay, out of which 2 years was as an assistant professor at Veltech University, Chennai. Okay. After that, I have been a technical engineer at Trident Tech Labs Private Limited, Chennai, for embedded project products. And then I have been an embedded developer with Broadgate Technical Services, again in Chennai. And then have joined Intupel Technologies as a field application engineer for Cadence products alone. Okay. And I used to support pan-India customers, both on tool point of view as well as on projects. Okay, it's only about tool support, but not about designing any projects or doing any projects. Okay, so right now I've been into customizing design, design of standard cells and standard cell layout design, etc. Okay, for the past 6 to 7 months, and I've been actively involved in training both students as well as professors on customized design flow, okay, involving standard cell design. Okay, so let us move into the agenda today. So we'll start with a brief introduction about Ntuple and about Cadence, and then we'll start with AMS Design Flow. So initially, I'll be giving you a small example of a buffer, okay, as of how to design an inverter on Virtuoso, which is one of the tools for used for customized design, and then how to import a .v file, that is a Verilog file, into Virtuoso, and how to combine uh, a block that has a CMOS inverter and an inverter that we had created using a .v file. Okay, how to combine those things and how to run the simulation. So this is the level up to which we are going to uh, be uh, s- uh, taken you through throughout the sessions. Okay, so I have been given two sessions, right, from 10 to 12 and then from 2 to 4. Okay, so that in the first session, we'll be discussing about the theoretical aspects, and in the second session, it will be demonstration, both on system point of view as well as IC design point of view. Okay, so illustration will be given on ARCAD PSpice as well as Cadence Spectre and Virtuoso. Why ORCAD and why Cadence Virtuoso? Okay, so as we move on, we'll be illustrating all these things, and then we'll moving. Once we get an idea about the AMS design flow, we'll move into the backgrounder for today's example design, that is SAR ADC. So one of the important blocks in a SAR ADC is a digital to analog converter. Okay, a resistor-based digital to analog converter. How to design that, and functional verification of digital to analog converter, and then we'll move into the successive approximation register-based ADC blocks and its functional verification. Okay, so this will be today's flow. In up to 12 o'clock, we'll be discussing about the theoretical aspects along with the small demo on AMS design flow. And then we'll move into the concept for the demonstration part in the second session. From 2 to 4, we'll have the demo on ARCAD PSpice as well as on Cadence Virtuoso. Okay, hope that is fine with all of you. So let me move into the introductory part. Okay, so Ntuple is a design service, product and engineering solution provider in cutting edge technologies, and we have our foothold in academics, aerospace and defense, public sector companies, as well as automotive electronic companies, as well as research labs like DRDO, BHEL, BEL, etc. And then we also uh, uh, act as consulting. We also provide consulting services for on-site and online training programs, both for academics as well as corporates. Okay. So our core values include integrity, excellence, agile and responsive. We stay united and focused, socially and environmentally responsible. So our main aim is to bridge the gap between industry and institution. Okay, so why in the sense, because most of the students nowadays don't have an idea of what is happening in an industry. Okay, just they learn the theoretical concepts, and most of them will not be having an idea of how to enter into company. Okay, what are the prerequisites, what are the requirements. So what they do, after 4 years of graduation, they go for some training or company, consulting institute. Okay, and then spend some more money. Okay, and then get employed with a little bit of idea that is provided over there. So rather than that, why don't they do it in institution itself? Because nowadays institutes provide almost colleges provide almost all the cutting edge technologies, all the tools, EDA tools that are required in order to gain adequate knowledge on the technical aspects, and to test or to measure and to design and check whatever is learned in books in the tool. Okay, they can do it hand in hand. Okay, so all the facilities are provided by the institutes, but the students don't make use of it. So these kinds of FDP programs and internship programs, etc., will help them in bridging those gaps. Okay, so what we do is we take the theoretical background of basic electronics. Okay, and then try to uh, do the same thing on the tools and show them the illustration. This is what happens. Okay, so that is how we act as a bridge between industry and institution. Okay, and these are the domains in which we work on: mechanical, computational fluid dynamics, electromagnetic systems, semiconductors, e-mobility, PCB design, PCB prototyping, 3D printing, indented tests, vector network analyzers, RF solutions, cybersecurity, Internet of Things, and power electronics. We have our foothold in all the major core domains, okay, which are evergreen. Okay, and this is a bird's eye view of Ntupel. Ntupel Technologies was incorporated in January 1st, 2010, and we are a 11-year-old company headquartered at Bangalore. We have our regional offices at Delhi, Pune, Ahmedabad, and Hyderabad. The team size is over 135, with a staff split of 35 sales executives and 75 technical engineers, along with 10 administrative uh, uh, staffs. Okay, so you can see the ratio. Okay, sales, the number of engineers and technical team are more than there's number of engineers and sales team. Okay, so that is how uh, we describe ourselves. We work on almost all the uh, domains. Okay, and we cover all the basics, uh, along with the adequate knowledge of tool. Okay, always tool knowledge is an added advantage, but the mandatory thing is basics of electrical and electronics engineering. Okay, electrical and electronics engineering, in the sense it covers both analog and digital electronics. Okay, so without that, having a tool knowledge alone won't help the upcoming engineers. So both should go hand in hand. Okay, so we help you in all those aspects. So these are our channel partners. We are the official academic channel partners for Cadence. Along with that, we also have tie-ups. We are also channel partners for ANSYS, Ritsu, Bungard, um, ORCAD, MITS Electronics, Niveti Systems, Nanatom for IoT products, electronic e-mobility, Semicron, and Excel VLSI for the training aspects. Okay, so about Cadence, so everybody should be having an idea about Cadence. It is an EDA provider. Cadence is an EDA provider who are industry leaders for more than 30 years. So its customers base includes hyperscale computing, 5G communications, automotive, aerospace, industry, and health. And its core interest is providing solutions for semiconductor and system design companies. Okay, it provides almost every tools that are required for that provides end-to-end solution like silicon design creation, simulation, implementation, and sign off of analog and digital circuits along with IC packaging. Okay, so these are the solutions provided for custom IC design and PCB design. Okay, so we start with Virtuoso. Okay, Virtuoso for schematic design entry. Okay, and then in order to check for its functional behavior, we have a tool called Spectre. Okay, so that is what we can see here. Okay, Virtuoso for schematic entry, and Spectre for testing the design as of how it responds for a given input. Okay, so then once you are done with these two steps, you will be moving into the layout part, physical representation of the design. Okay, and then you'll be moving into the verification aspects for which we have a leg sorry for which we have PVS as well as Ashura. Okay, and then once these things are done, you will be moving into characterization. Okay, that is you'll generate some cells on using Virtuoso, and that has to be made use of in digital designs. Okay, so for that you need to develop or you need to um, generate certain library cells. Okay, so library files. So Liberate is used for such a purpose. Okay, and then once you have fabricated your IC, you need to test it on board level. Okay, so for that we have Allegro. Okay, and for sign-off analysis we have Sigrity as well as Allegro. So almost the solutions work for mixed signal, analog and RF, and for advanced nodes, right from advanced nodes like 16 nanometer, 5 nanometer. So currently, even 3 nanometer chips are available, but not in the market. Still, research is going on. Okay. Along with that, it also provides support for rigid, flexible board enablement and advanced packaging. Okay, so all these tools that are given here are market leaders for over 25 years. Okay, so these are the solutions provided for mixed signal and low power solutions. Okay, so either you can have the analog design on top, and or you can have the digital design on top. That is what we call it as analog on top and digital on top, mixed signal design. Okay, so you have the respective tools, but which is used for analog part, which is used for a digital part. As we move on, we'll be illustrating those things, or we'll give the list of tools which are provided for analog domain as well as for digital domain. Okay, so these are the tools for digital design and sign off. Okay, you will be starting the digital design with design entry, right? So for design entry, you need a tool called Incisive, okay, which will help you in compilation, elaboration, and simulation. Okay, so once your program is compiled and simulated, you can move into, you can create a block level design of that. Okay, so for that you need a tool called Genus. Genus and Stratus will be helping you in converting your HDL into a block level or module level design. Followed by that, you'll be moving into the timing, area, and power analysis for your circuit. Okay, that will be taken care of by a tool called Tempus, which is for timing sign off, and Voltus for power sign off. Okay, and once these things are done, you will be moving into design for testability, which you call it as DFT. So Modus will help you in those aspects. So it will help you in inducing faults to your design. So you may have an idea about stuck at zero fault, stuck at one fault, built-in self-test. So how to induce the faults in the design, and how to uh, test its impact on the circuit. So Modus gives you an idea about that, and Genus and Modus both work hand in hand uh, in for DFT. Okay. Along with that, you also have tempers and volters in order to check the power and timing constraints of the design. Okay, and once this is done, you will be moving into the physical representation of the design, for which you need a tool called Innovus. Okay, for physical implementation of the design. Once you complete the physical implementation, that is going through floor planning, power planning, placement, clock tree synthesis, and routing, you need to verify the design as per the physical set of rules provided by each and every technology node. So for that, you have a sign off tool, which is the same thing as we have seen in full custom. It is Ashura or PVS, and Quantus is for checking the impact of parasitic components. Okay, so once these things are done, you will be moving into the conformal process. That is, you'll be checking, uh, you'll be comparing the net lists, okay, as of which are the nets or ports that are added in addition to your original design. Okay, so conformal helps you in those aspects. Okay, so all these tools provide you with uh, parallel processing. Okay, it doesn't wait for any of the inputs. So with whatever inputs are available, it starts doing your process and provide you with the output at each and every stage. Okay, and it is more accurate. Um, Cadence is one of the industry standard tools where almost all the semiconductor design industry make use of Cadence in order to ensure that their uh, ICs are error free or bug free. Okay, so along with that, it also supports the digital and mixed signal flow of design. Okay, so this is about the solutions that are provided by Cadence in order to support your analog design. Excuse me, analog design and digital design. Okay, along with that, you have certain value added services that are provided by Cadence, like online support and rapid action kits, which will where you'll be provided with an example design in order to get used to the tools. Like if you take genus, okay, in order to get used to genus tool, you'll be given with an example design, and each and every steps will be provided with the screenshots, and it also supports generic PDKs. You'll also be provided with training bites and custom training programs as per the requirement of a customer. Okay, whatever they are expecting. Okay, now we'll get into the AMS design flow. So it is about combining two design process, okay, both analog and mixed signal. So why is this required? What is the necessity or what is the requirement of an AMS design flow? Anybody from the crowd? You can unmute yourselves and let me know the answer, or you can uh, let me know on the chat. Anything is okay. Why is mixed signal design most important? And let it be an interactive session, otherwise we'll lose interest. So you can unmute yourselves and let me know your answer, or you can also type it on the chat box. Think I have access to the chat.
Participants, your mute also your mic also enabled, and or else you can use the chat box.
So feel free to give your answers on the chat, or you can unmute yourselves and let me know your answers. Why mixed signal design is finding its importance more often, very often. Yes, yes, participants. Anyone? Fastest growing market in electronics and semiconductor industry. Okay. Anybody else?
There is no more answers. You can continue sessions.
Yeah. Okay. Thank you. So let us consider a general example of a mobile phone. So for a mobile phone, okay. So you may give an audio signal as an input, okay, through a microphone, and an image also as an input. So what are these signals? For example, consider an audio signal. So an audio is an analog or digital signal. It is an analog signal, right? And similarly, whatever you see, whatever you hear, everything are analog in nature. But your um, your mobile phone captures the audio signal. It processes it because you may have some noise. Okay, so all those noise are filtered, and it is sent to the receiver, sent to the person at the receiver end. So between this, right from capturing the audio signal to transmitting the audio signal over a large distance. Okay, so what are there? You have amplifiers, you have mixers, you have image enhancers, you have audio enhancers. Okay, so all these blocks in one way or the other, they are trying to process your analog signal. Okay, they are trying to enhance your analog signal, or it is trying to reduce the noise. Okay, and even if you check on the image or video that is captured, okay, at some points your image can be enhanced. Okay, the image quality can be enhanced at So nowadays you can see an image which is colored at certain point and blurred at the corners. Okay, so for all these things you need an IC that has to do all these things with the help of an algorithm. Okay, so all these process of image enhancement, audio enhancement, encoding, encryption, decryption, everything are processes of digital electronics. Okay, so it is a combination of both analog as well as digital modules. Okay, so that is the reason why mixed signal design is becoming more prominent nowadays. Okay, so when you're trying to design go through an analog design flow, it is going to be netlist based and it is mainly manual. Whatever is based on analog, okay, it is manual. You have to do everything manually. You have to capture the design. You have to uh, uh, you have to select each and every process. You have to uh, uh, for example, if you are going for a layout, okay, it cannot be automated. Okay, you have to do it manually in order to enhance the quality of uh, the particular layout. Okay, so so analog design flow is what we call as full custom. Okay, because it is very critical, and it is time consuming, but the designer has an idea of what might be the errors and how to clear those things off. But when you come to digital design flow, it is HDL based and they are highly automated. Just give a script or give a program, the tool does all the things for you. Okay, so analog module can be made use of in digital by using standard cell libraries. Okay, uh, and the digital modules also can be made use of in analog by converting the HDL into a symbol. Okay, that is what we are going to see today. Okay, so what about full custom and semi-custom IC design flow? Okay, so in order to get into a mixed signal design, first you should be having an idea of what is a full custom IC design flow and what is a semi-custom IC design flow. Okay, so based on the market research analysis, okay, the market research analyst will be in close connection with the customers, right? Customers or end users. So based on his inputs, like um, the processing time has to be faster, okay, or the audio quality or the video quality of your mobile phone or your television or uh, your refrigerator, your washing machine. Okay, so the market research analyst will be in close interaction with the customers. So from based on his inputs, the designer will start working on the designs. Okay, so what will be the starting point for any full custom IC design? Okay, so that will be the specification based on the data provided by market research analyst. So once you get the specification, you start working on paper. Okay, so whatever is the design, okay, first you have to work on it on paper. Okay, and then check what is going to be the input, how is it going to be given, what might be the effects or what might be the disturbances at the input, how are they going to be filtered out. Okay, and then what is the actual functionality of the circuit. Okay, whether it is getting retained or it's getting changed. Okay, and if it is getting changed, how is it getting changed and how to bring back the original response. Okay, so checking all these things on paper is the first step in designing. Once you complete everything on paper, you bring it to the tool. Okay, and that is what we call as a schematic entry, and Virtuoso schematic editor provided by Cadence will help you in that part. Okay, once you have completed the design entry, you need to check as of how it behaves, okay, how the circuit behaves by giving some inputs. Okay, so that is what we do in simulation. When you talk about simulation, you have two steps. You first check about how the circuit responds, okay, or whether the circuit responds or not for the input given, okay, and then you will move on into whether the response is functionally correct or not. Okay, so first you'll have to check whether the circuit is responding or not, and then you'll have to check whether the response provided by the circuit is functionally correct or not. And for that, Cadence provides you with a tool called Spectre, okay, which is a multi-mode simulator, and it has it can help you in simulating different types of circuits like spice circuit and mixed signal design, or basic schematic and schematic as of a transistor level design, or circuit active or passive components based designs, etc. Okay, so once you are satisfied with the output of the circuit, okay, you may go into the layout part. So layout is called the physical representation of the design. Okay, because when you are working on schematic entry, for example, if you are using CMOS technology, then you will be mentioning a value of length, a value of width for your NMOS or PMOS transistor. So those things will be for a symbolic representation of a MOSFET. But how does it look like on chip? A fabricated MOSFET will look like uh, how will it look like based on the length or width given by you, okay, in your schematic entry. Okay, so in order to get that idea, we go into layout. Okay, so that is the reason why we call it as physical representation of the circuit. And virtuoso layout editor will help you in that part, okay, in doing your layout. Once you have completed your layout, you move into the physical verification part. Okay, so physical verification in the sense, each and every technology node will be having their own set of rules for each and every layers. Like if you talk about layout, you'll be working on a metal layer, a polysilicon layer, because you would have gone through the P stub or N stub process. Okay, so you have different layers, right? A polysilicon, metal, silicon dioxide, N well, P well, and uh, N implant, P implant, metal layers, different types of metal layers. So each and every layer will be having their own set of rules, like minimum size, minimum spacing. Okay, in order to avoid some effects. Okay, so those rules are called design rules. Okay, so the first step you'll be starting with checking out those design rules. Okay, whether your layout has been designed by considering those design rules. Okay, like minimum space, size, and minimum spacing. Okay, that is what we do with design rule check or design rule compliance, and that is what we call as DRC. And the next step will be you have a schematic. Okay, and the layout is a representation of schematic, physical representation of your schematic. So whatever is there in your schematic should be replicated in your layout also. Okay, so like interconnection devices, ports, input ports, output ports, etc. So comparing your schematic with the layout is what we call as layout versus schematic. Okay, so in case if you find some devices left or some interconnections missing, then you can again go back and redo it once again and save it, then again come for DRC LVS. Okay, once your design is DRC and LVS clean, you'll be moving into the next step, which is called parasitic extraction. We call it as RCX or RC extraction. Okay, so what are parasites first of all? So whatever process you have, first think about it in uh, first compare it with your day-to-day activity. Okay, don't just go into technical concepts. Think in a general manner. So generally, what do you mean by parasitics, or what do you mean by parasites? Anybody from the crowd? What are parasites, or what are parasitics? So anybody on the chat? Okay, fine. So nobody is responding. Once again, I would like to let you know that if it is an interactive session, then it will be even more interesting. Okay. So uh, a component or a substance that is not there physically, that is not present physically, but it can its impact is already there. Okay, and it is not, it is dependent on other things for its working. Okay, so how is that for example, a mushroom? Okay, mushroom cannot prepare its own food. It is dependent on other plants for its food. Okay, so likewise, how does this comparison work with an IC design or a circuit design, you may ask? Okay, so let me explain. We were talking about different layers, right? uh, and if you look at the layout, so all the layers will not be arranged in a planar manner. It will be placed one below the other and separated by a fair distance. Okay, and the gap between two layers will be filled up by an insulating material. Okay, insulating material in the sense, you may know it might be silicon dioxide or any type of dielectric material. Okay, so it is because of those layers, its properties, its characteristics. Okay, the gap between two layers. Okay, and the media that is present between two layers. So because of these things, the dimensions, okay, because of these things, certain components get generated automatically, like a resistor, a capacitor, a diode, bipolar junction transistor, an inductor. Okay, so for example, let me give you an example. If you have a path segment that is connecting two terminals of two different components, okay, and if it is of higher width, for example, imagine if it has a higher width, okay, then obviously the resistance increases. Okay, the resistance provided by that path segment increases. Okay, so how is that indicated? By a parasitic resistor. Okay, and just imagine that you are trying to connect two different layers, like a metal layer with a polysilicon. Okay, so you need a via, okay, which acts as a connector. Like you can imagine a plumber who is trying to connect two pipes of different diameters. He'll be making use of a coupler, right, or a coupling, or an L bend or a T bend, etc. Okay, so those components are used to connect a coupler or a L bend or a T bend. They are used to connect two pipes of different diameters. So likewise, we use via in order to connect two different layers, establish connection between two different layers. As per the example that I have told you, if you are trying to connect metal with a polysilicon, okay, so you have the metal layer first, and then you'll be having an insulating layer, okay, and then you'll be having a polysilicon. Okay, so what is that? uh, so polysilicon is also a conductor, right, at whatever threshold voltage we provide. Okay, for example, if the threshold voltage is zero point 0.7, okay, then it will act as a conductor when it has an input of zero point 0.7 volt. Anything above that or below that, it's not going to be acting as a conductor. Okay, so a metal is already a conductor, and then you have a polysilicon, and these two are separated by an insulating material. So what is this? This is a capacitor, right? Okay, two metals separated by an insulating material or a dielectric material is already a capacitor. So this guys gives rise to a parasitic capacitance, and its values are dependent on the dimensions of the layers, spacing between the layers, etc. Okay, so this is how parasitic devices are formed, and to check the values of those parasitics and where all they have been included or where all they are getting formed. Okay, so that is what we do with parasitic extraction. Okay, so for physical verification process like DRC and LVS, and for parasitic extraction, we have tool called Ashura that is provided by Cadence, and for lower technology node we have a tool called PVS. Okay, so to check the impact of these parasitic components, we redo the simulation. Okay, so how do we redo the simulation? We we import these parasitic resistance capacitances or these parasitic devices on the schematic once again. Okay, so this process is called back annotation, importing the uh, parasitic resistances and capacitances from the layout back into the schematic. Okay, and to check its impact we rerun the simulation. Okay, so this process is called back annotation. If the impact is huge, okay, then you rework on the layout. Okay, or else you go ahead with the flow. Okay, so for the back annotation process, again you go back to the Virtuoso schematic editor and Spectre. Okay, and once this is done, once you are satisfied with your overall design, you generate the GDS file. So what is the GDS file? GDS stands for graphical data stream, and II stands for information interchange. Okay, so this provides you with the information of the layout, layer map file, okay, ports, okay, etc. Okay, GDS file provides you with those kind of information, and Virtuoso is made use of for GDS file generation. Okay, yeah, so this is about the full custom IC design flow. Any doubts till now? Any doubts till now, participants? If there are any doubts, you can let me know on the chat, or you can unmute yourselves and let me know your queries. Okay, so
There is
Kokila
no
says
doubt.
no. Okay, fine. So we'll move further with the semi-custom IC design flow. Okay, so you can now have a list of tools. Okay, as of what all are made use of for full custom IC design, the Virtuoso, Spectre, and Assure or PVS. Okay. And now coming to the semi-custom IC design flow. So Cadence is the market leader in semi-custom IC design, okay, and testing, sign off, etc. Okay, so for design entry, starting point will again be the data provided by market research analyst, and based on that, you'll be working on a specification, and for that specification, you'll write a program, okay, using any one of the HDL languages. It can be Verilog or VHDL or System Verilog or C program, System C, etc. Okay, so once you have completed the RTL design, okay, you'll be working on the functional simulation. Uh, it is not, you cannot directly simulate your project, your design, right? So first you need to go through the compilation. So what is compilation? To check the syntax and semantics, whether you have written the program based on the basic syntax of uh, the HDL designing. Okay, so for that you go into the compilation part. Okay, and in your HDL program you would have mentioned certain logic. You'll be using some expressions, arithmetic expressions, logical expressions. Okay, So your tool has to identify, or it has to understand as of what that refers to, right? So for that you need to map your HDL with the tool, okay, with the help of some libraries. Okay, so this part of mapping the HDL with the tool is called as elaboration process, and then you simulate. Okay, you check the impact, or you check how your RTL design responds to a particular input. Okay, so for that you work on the functional simulation. So for these aspects, HDL design, and then going into compilation, elaboration, and simulation, you have the tool called Incisive helping you out. Okay, that is provided by Cadence. And then once you are satisfied with your simulation results, what you can do is you can move into the synthesis part. So what is synthesis? You have written an RTL program, okay, and it has to be converted converted or translated into a block level design, or a logic level design, or a transistor level design, etc. Okay, so for that translation, we use a tool called Genus synthesis solution. Okay, and for advanced technology nodes, you have a tool called Stratus. Okay, so for synthesis, translating your HDL into a block level or module level design, or any type of logical representation, okay, you have the tool called Genus, and that process is called synthesis. Once you synthesize your design, you need to check for the timing, area, and power. We call, in short, we call that as TAP. Okay, so what are the gate to gate delays, what are the net to net delay, what are the input to output delay, okay, propagation delay, whether it is rise time or a fall time, what is the slack involved in the design, what is the slew involved in the design. So all these things can be checked out. What is the power consumption, what is the static power dissipated, what is the dynamic power dissipated, uh, where, in which module, in which net. Okay, and then area. What is going to be the approximate area occupied by the design on the silicon wafer? Okay, so these things can be checked out after the synthesis stage. Okay, and for timing sign off, Tempest will help you out. For power sign off, Voltage will be helping you out. Okay, and then once you are satisfied with these results, you move into the design for testability process. We call this as DFT in short. Okay, so if you are talking about DFT, so you will start inducing the errors, okay, and check for its response. For example, just imagine that you are designing an inverter. So what is the functionality of an inverter? If you give 0 as an input, 1 has to be the output, just the inverse. Okay, so instead of 0, okay, instead of for an input 0, instead of 1 at the output, if you still get a 0, okay, that is what we call as stuck at 0 fault. Okay, within a fraction of second, if you give 0, the output has to be 1, but if it is still at 0, then you have a stuck at 0 fault. Okay, so it is not actually there, but you are inducing the fault. Okay, so for example, for a delay of 10 nanosecond, or for a delay of 20 nanosecond, my output should still be in 0, and only then it has to go to 1. Okay, like that. If you're trying to induce an error, okay, that is how we do it. Okay, so why do we induce error and check for the response of design? Okay, so it is to check how far your circuit is reliable. Okay, so what is the meaning of reliability? Any idea about reliability? What is reliability? Anybody from the crowd? And why do we go for that check? Reliability check. What is a reliability check and why we do it? Yes, you can unmute yourselves and let me know the answer, or you can give it on the chat. Anyone from the crowd? Anybody? Please respond. Participants, anybody? Okay, fine. So for example, just imagine that you are purchasing a mobile phone, XRC. As we move forward, I'll explain that. Okay. So right now my question is about what is reliability and why we go for a reliability check. Okay. So reliability in the sense, for example, just imagine that you are buying a mobile phone. Okay. So and you'll not be throwing it off over a week or a day. Okay, you'll be trying to make use of that mobile phone as long as possible. Okay, so irrespective of when it is purchased and irrespective of how long it is being used, okay, so the input time, the quality of the mobile in the sense, when you do work, when you try to make a call, okay, how your audio is being heard at the receiving end, whether it is clear or you have some disturbances, how authentic your audio is, okay, and what is the quality of your camera, okay, when you capture a video, how clear it is, okay, and in case if you are willing to do some work on your captured image or a captured video, okay, so how does it work, or how is the result over the years of usage. Okay, it should be the same. Okay, otherwise there is no point in uh, purchasing that mobile, right? Or if it falls down, the parts should be easily available, and it should work fine even after replacing certain parts like display panel. Okay, so that is why we go for a reliability check. Okay, and irrespective of the conditions, whether it is 20 degrees Celsius or a 60 degrees Celsius, your mobile should provide you with the same kind of response. Okay, so that is the reason why we go for reliability check. So once you go for the once you do that with the help of DFT, okay, so you get an idea of how far your circuit will be alive or be able to provide you with a clear cut input and output. Okay, so that is why we go for a reliability check using DFT process. Okay, and then you can move into the physical design part. Okay, where this is similar to your layout that we had discussed in full custom IC design flow. Okay, and here the physical representation or physical design is split up into 5 steps. Okay, you'll start with floor planning, power planning, placement, clock tree synthesis, and routing. Okay, so let me give you a real-time example. Like you are trying to build a house. Okay, so before you start building a house, what has to be done? You have to purchase a land, right? And you'll be planning. Okay, whether planning about the available area. For example, if you have 1,000 square feet of land purchased, Okay, so you'll be deciding upon what should be the space for hall, what should be the space for what should be the space required for space allocated for a dining room, what is going to be the space allocated for a kitchen, what is the space allocated for a parking area, garden space. So for each and everything, you are going to plan it, right? This is how my house is going to look like. Okay, this is how I'm going to plan it. Okay, so that is similar to floor planning. So in a silicon wafer provided, you'll be deciding upon this is going to be the space for my power IC. Okay, step up or step down device, whatever it is. This is going to be the space for this is where I'm going to place my power IC. Okay, and this is where I'm going to place my image processing IC. This is where I'm going to place my SRAM. This is going to be the space for my DRAM, or this is going to be the space for my core processor. This is where I'm going to have my input ports and output ports, and this is where I'm going to have my USB port. Okay, like that. Okay, so you'll be deciding upon where are each and every component or each and every block of your design going to be placed. Okay, so that is what we call as floor planning. And then for your core design, you'll be having certain you need some power in order to activate your IC. Okay, activate your IC, or to power on your IC, or for your IC to start working, you need some value of voltage. Okay, so supply is going to be VDD, and your ground, the neutral, is going to be VSS. Okay, so deciding upon that, and the layers that are going to be made use of for your power lines, ground lines, what is going to be the width, what is going to be the length, how far is it going to be placed from your core boundary or IO boundary, whatever it is. So that is going to be power planning. Okay, and then you will be uh, translating your block level design or a module level design into standard cells. Okay, and that is what you do as a placement. Okay, only after floor planning and power planning you place your design. Okay, and then comes your clock tree synthesis. Okay, so if you are talking about sequential circuits, then you need clock signals, right? Okay, so clocks are going to be the activating part of your circuit. Okay, so without a clock input, your input won't go to the next level, or your device doesn't consider or doesn't take your input. Okay, so that is the reason why we have a clock tree synthesis, but in combinational circuits these are not required. Okay, so uh, that is to induce or to include clock signals to your design. We go for a process called clock tree synthesis, and you have certain algorithms that will be working in background in your cadence tool. Okay, so H tree algorithm, etc., or basic tree diagram algorithm, okay, that you can make use of for clock tree synthesis. And once that is done, you'll be going into the routing process. See, you have already done the floor planning, you have placed your power lines, you have got your overall design, and you have included the clocks. But are they connected to each other? The answer is no. Until the routing part, the your power lines, your design, core design, your clock signals, everything will be separated from each other. They are not interconnected with each other. So only during the routing part, the overall design gets routed, or the overall design gets interconnected with each other. Okay, so these are the 5 processes, and your Innovus tool will help you in uh, doing these processes, starting from floor planning, power planning, placement, clock tree synthesis, and routing. Okay, so once these things are done, you'll again move into the physical verification. So DRC and LVS we have already seen, design role check, and the layout was a schematic depending on the technology node. And along with that, you'll be doing the parasitic extraction also. So that is what we see as XRC. Okay, I had seen a question from one of the participants, which is XRC. Okay, so Pallavi Tyagi, actually, uh, this is not the session where we'll be explaining some power planning algorithms. Okay, you have, this is about mixed signal design. Okay, and you have a session by one of my colleague who is Kedarnath will be explaining about those things. And within a short duration of time, we'll not be able to explain all those things. In case if you need more details, then you can visit our website for short-term programs or internship trainings, etc. Okay, or career builder programs, which I'll be showing you as of how to check in our website. Okay, hope that answers your query. Okay. So XRC is parasitic extraction. So as usual, the physical verification process will be taken care of by tools like PVS or Ashura. Okay, and once you are satisfied with your design, you'll be moving into the GDS file generation. Okay, so we have seen the last three steps you have already seen in your full custom IC design, and it is the same thing. Okay, so in this semi-custom IC design flow, you have some other process like power sign off, okay, for which you have a tool called Oltus, and for timing sign off, you have a tool called Tempus. For linting, okay, you have a tool called Jasper and Conformal, etc. for the linting process. And then you have modus for DFT, modus and genus or stratus for synthesis, etc. Okay, so this is about the semi-custom IC design flow. Any doubts till now? Any doubts till now, participants? Okay, fine. So let us move further. So you have seen what is full custom IC design flow and what is a semi-custom IC design flow. So let us see how to merge both these things. Okay, that is for a mixed signal design on cadence. Okay, so it will be until the simulation process only because we don't have enough time for the layout part. So I'll just show you how to run the simulation. Okay, so let me go to the tool. Okay, so I have already opened some designs. Let me close them. Okay, so Cadence is supported only on Linux platforms, and that too especially with the Red Hat Enterprise Linux. Okay, RHEL, we call it as RHEL. Okay, and Cadence is not supported with any other operating systems. Okay, and it is partially supported with CentOS and Ubuntu, but it is at the customer's risk. Okay, Cadence doesn't provide support for those operating systems, software installed in those operating systems. Cadence provides support only for installation on Red Hat Enterprise Linux. Okay, so that is why we have that particular operating system. let me, before moving into the design, let us uh, create a separate folder. Okay, and we call that as a workspace. Okay, so to create a folder, what I can do is just make a right click and select create folder. So I'll name it as Kungunadu. Okay, okay, I'll name it as Kungunadu and click on enter to create that folder. Okay, so now open that folder. Okay, and the first thing is you have to open a terminal. Okay, so from that folder, just make a right click and go for open in terminal. Initialize a shell script, because the Cadence tool and the operating system has have certain libraries in common, and they are mapped together with each other by a shell script. Okay, so we are just initializing that shell script by the command csh. Okay, so now source a file called cshrc. So source space slash home slash car slash cshrc. Okay, cshrc stands for shell script run command, and the cshrc2 is the name of my cshrc file. Okay, so what is the necessity of sourcing a cshrc file? Okay, so the cshrc file uh, contains the information about the uh, tool installation directory. Okay, in which folder of your RHEL system is your tool installed. Okay, because you need to open the tool, right? So if you are trying to open a tool, from where it has to be opened. Okay, so we call that as invoke. Okay, tool invoke. Okay, so before you open a tool or before you invoke a tool, you need to source this CSHRC file. So once you type this command and click on enter, so you'll be getting a command prompt like this: welcome to Cadence Tool Suite. And I need the tool to be open. The tool that I have to open is Virtuoso. So I'll just type VIRTUOSO space ampersand Virtuoso. Okay, I'm going to open Virtuoso. So the commands are case sensitive. Okay, so please type it carefully. So the command has to be Virtuoso space and ampersand. Without ampersand also, it's not a problem. So just if you click on enter, okay, I'll get the tool open like this. Okay, so this is called a command interpreter window. So you can see the Virtuoso framework license was checked out successfully, and the total checkout time was 0.03 seconds. Okay, so from this command interpreter window, what you can do is you can go to tools, and under that you'll have to select library manager. So under tools, select library manager, and you can see three columns. Okay, library, cell, and view. So under library, you can see the predefined libraries that are provided by Cadence. Okay, here itself you can see GPDK 45, 90, and 180. The three technology nodes that are provided by Cadence by default. Okay, right now it is providing 45 nanometer, but we Intupel Technologies are providing 90 nanometers as well as 180 nanometer also, in order to get a fair bit of idea or hands-on experience on those technology nodes also. Okay, so if you select a particular technology node, then you can see the devices or components that are available for each and every library. Okay, and these devices or components are called cells. Okay, so if you select a cell, then you can have a look at the libraries or the type of view that is available for that particular cell, or for a particular device. Okay, so that is what we can see here: symbol, spectre, transform, v, verilog, etc. Okay, so like this, you need to create your own library. Okay, and create your own cell and create the respective views, what all views you need. Okay, so that is what we are going to do now. So to create a library, I'll go for file, new, and select library. Okay, so I'm going to create a buffer. Okay, so for creating a buffer, first I'll build a CMOS inverter, and then I need two inverters, right? So one of the inverter is going to be based on CMOS technology, and the other one is going to be based on a HDL program. Okay, for example, I'm going to take Verilog. Okay, so I'll name the library as one underscore buffer. Okay, don't make use of space in between. Okay, instead of having a space, I am making use of underscore. Okay, and case sensitivity, if you are giving anything in capital, then it has to be in capital. That is what Linux is all about. Linux is case sensitive. Okay, so give a name for the library and click on OK, right? So at the bottom, you can see technology file. So you have three technology nodes already. I'm going to work based on any one of those technology nodes. So I'll go to the third option, attached to an existing technology library, select OK. And here you can see the list of technology libraries. Under technology library, you can see the list of libraries. So I'm going to work on GPDK 180. So I'll select GPDK 180 and click on OK, right? So you can see the library created over here. Under library, this is what you had created just now. Okay, so under that you haven't created anything. Okay, so that is why when you have selected that library, you don't see anything. Okay, but if you select any other things, you can see because they are already available. Okay, this is what I have created just now, and there are no cells inside that. So I'm going to create a cell now. So for that, I'll select the library that I have created in order to get the cell under that particular library. Okay, so I'll select the library first, and then I'll go to file, new, and select cell view. I'll name the cell. For example, I'll name it as one underscore, or I'll just name it as CMOS inverter. Okay, and I'll click on OK, right? So this is how a Virtuoso schematic editor looks like. So at the top, you can see Virtuoso schematic editor L editing. Okay, and this is the name of your library. One underscore buffer is the name of your library. CMOS inverter is the name of your cell, and schematic is the type of view that you are creating. Okay, so I need to include an NMOS and PMOS transistor because it is going to be CMOS technology. So to include a transistor, including a transistor or any kind of devices is called adding an instance to the particular circuit. Okay, so for that I'll go for the shortcut I. Okay, if you click on I on the keyboard, then you'll get an add instance window like this. So next to library, you can see a drop down. So if you click on that, you can see the technology libraries. So I had selected GPDK 180, right? So select GPDK 180, and under cell, you can choose NMOS. Okay, because I need an NMOS transistor, and the view is going to be simple. Okay, so if you click on tab, okay, you can see the length, the width, the finger width, number of fingers, etc. Okay, so as of now, I'm going to make use of the basic or the default parameters. I'm not going to change anything. If required, you can change, no issues. Okay, but here for this example, I'm not going to change anything. So I'll click on hide and place it over here. And similarly, I'll place a PMOS transistor. Okay, so click on hide and I'll place the PMOS transistor. Then I need the input and output pins or ports. Okay, so for that, I'll go for the bind key called P. P for Pondicherry. I'll click on P. So I get an option called create pin. So here I can name my pins. I can name any number of pins at the same instance of time, uh, but I need to separate them with the spaces. Okay, so for example, I'll name all my input pins. So A is going to be my input, VDD is also my input, and VSS is also my input. Okay, our VDD and VSS can be taken as in out also. Just below names, I can select the direction, whether it is going to be an input pin or in out pin or an output pin, whatever it is. So I'll choose the direction to be input since all these pins are input pins. So click on hide and you need to place them in the same order. So first ADD, VDD and ADD, A, VDD and VSS. So first I'll place my input pin. Then I'll go to the top. If required, I can rotate the pins by using the shortcut R and just make a left mouse click to place it. Again, I need to rotate this and I'll place it here. Okay, fine. So if required, you can select and move it also. Okay, no issues. So input pin, VDD and VSS are there, but I need an output pin, right? So again, I'll go for add pin and I'll name the output pin as Y. So this is an output pin, right? So I'll change the direction to output. Click on hide and I'll place it like this. Okay. So now I need to do the connection. So for that, I'll make use of wire. Okay. So for wire, I need to use the bind key W. Okay. Click on W. Make a left mouse click at the starting point and a left mouse click at the end point. Okay. So these connections are done. And then my input. Okay. And then my output. Fine. And I'll short my bulk with source terminal to avoid body effect. Okay, so now I have completed my transistor level design. Okay, I'll check and save. You have two options. One is just save, saves your design as it is, and the other one is check and save, which checks for any floating component or floating nets. Floating nets in the sense whichever is left unconnected. Okay, so to check those things, I go for check and save, right? So my circuit is now saved, but are there any errors or warnings? How to check that? I need to go back to command interpreter window. You can see at the bottom, you can see the Virtuoso tab. So just make a click on that. Okay, so you can see the last 2 to 3 lines. So schematic check is completed with no errors and the circuit is saved, right? So now I'll again open the CMOS inverter, right? I'll create a top level hierarchy for that. Top level hierarchy in the sense I'll create a symbol for this. So for that I'll go for create and under that I'll go for cell view, select from cell view. So you can see the library name. So this is the library. This is the cell name for which I have a schematic already. From a schematic, I'm going to create a symbol. Okay, so that is what is mentioned here as from view name and to view name. Click on OK. And here you can see the pins. So on the left hand side, I am going to have my input, which is ADA. On top, what I can do is I can just cut this. Okay, so you can just cut this. On right hand side, I'll have my output pin Y. On top, I'll have my VDD, and at the bottom, I'll have my VSS. Okay, so on all four sides, I'll have 4 pins. Click on OK so that you can see a default symbol. So this is how your symbol looks like by default. But what is the actual symbol of an inverter? A triangle with a bubble in front, right? So what I'll do is I'll select this inner rectangle. So how do you select? Just make a left mouse click so that it gets selected. Click on delete to remove that. You have the drawing tools over here like create circle, create polygon, create ellipse, create line, create an arc, etc. So to create a triangle, I'll go for create line and I'll just draw, just like wiring, I'll just draw the triangle. Okay, and I'll place a bubble. So for the bubble, I'll go for create circle. Okay, so just make a left mouse click on create circle. Just click and expand. Okay, so I get a triangle with a bubble in front. Check and save your symbol. Okay, so you can go back to command interpreter window and check I don't have any errors. So that's it. So after checking and saving, you can close this symbol. Okay. So I can close this transistor level design also. Now, if you come back to your library manager, you can see. So under one underscore buffer, the library that I had created, I have a cell now. And for this cell, I have created two views. One is the schematic and the other one is symbol. So this is the reason why we call it as custom IC design. We create everything manually, okay, as per the requirement. Okay, there is no automation involved here. Everything is done manually by the designer. Okay, so next, this is a transistor level design. Now I am going to import a HDL based design. So how to create the file? I'll just go to the directory, okay, that I created earlier. I created a folder called Konkunadu, right? So I am going back to that folder. From this, I am going to open a terminal, okay, and I'm going to create a blank document. So for that, I'm going to make use of an editor. So gedit is the most basic text editor in provided by Cadence or any Linux environment. Okay, along with gedit, you have VI editor, Vim editor, etc. Okay, you have a number of editors. You can select any one of them and give a name for your file. So I'll name it as inverter.v. So Verilog is going to be the extension for my HDL language that I'm going to make use of. Click on enter. So it will create a blank document. So here I'll type my program. So for example, so module, I'm creating a module INV. Okay, INV, and within braces I'll mention my input and output ports. I'll define the input ports now. So input is going to be A and output is going to be Y. Now I'll assign the operator. Okay, assign Y is equal to, it's going to be negation of A, right? Inverse of A, right? So I'll assign the operator and then I'll end the module. That's all. A simple Verilog program for an inverter. That's all. Okay. So I'll save this file. Okay, you can see the save option over here. Save this file and you can close it. That's all. I have created a .v file and you can see this here. Okay, now I have to import this into Virtuoso. It doesn't mean like just you have created, just since you have created a .v file within the same directory itself, it gets included to Virtuoso. No, you have to import it. Okay, so for importing it, I'll get back to my command interpreter window. And from here, I'll go to file. Okay, and then I'll go for import. Under import, I'll choose Verilog because whatever I've created is a Verilog file, right? So I'll go for Verilog. So here I'll have to browse the file to be imported. I have the browse option over here. So click on that and select the .v file. So I'll select the inverter.v file and click on open. Then I have the target library name. You have the browse option over here. Click on that and select the library in which that .v file has to be imported. So I'll select the library, click on close. Okay, that's it. So schematic view name is schematic, netlist is netlist, and you are going to create a functional view. Okay, I'm going to create a symbol only. Okay, other options, import as functional. Functional view will be created by default, but symbol you'll have to let the tool know whether it has to be created or not. So once these things are done, you can select OK. So you can see Verilog import process has started and it is completed. Verilog import completed. Look at the log file. So if you click on yes, you can have a view at the log file. You can see using NC Vlog. As I have told already, all the tools provided by Cadence are interoperable. So here the insistive tool is being made use of for compiling your Verilog program. NC Vlog is the Verilog compiler that comes under incisive. Okay, so Cadence makes use of the Verilog compiler, compiles the program for compilation. Okay, and it has created a symbol, checked in symbol inv. Functional view also is checked out. Okay, and the symbol is created. So now if you go back to the library manager, just click on this uh, library that you had created and select it again. Okay, so you can see the CMOS inverter, which is the transistor level design, and INV, which was imported now. So here you have a functional view, nothing but your program. Okay, Verilog program, and your symbol. This is the symbol that is created. Okay, now you are going to combine both of these blocks and form a design. This is going to be your mixed signal design. Okay, so for that I'll create a cell view. I'll go to file, new cell view. I'll name it as buffer. Okay, and click on OK. I'll instantiate the CMOS uh, inverter, or whichever it is. I'll instantiate any one of those things. Inverter first, click on close. I'll place it here, and then the CMOS inverter. Click on hide, and then I need an output port. I'll go for add pin and name it as V out, V underscore out. I'll have this as my output port. Then I need input source. Input, I'm going to give a pulse. Okay, input pulse is what I'm going to give. Step response, continuous step signals, unit step signals. And then for VDD, I'll have a supply voltage of say around 3 volt. For VSS, I'll have a ground terminal. So how to get those sources? I'll go for add instance again. Under library, I can see analog lib, okay, which has all the sources, generalized sources, which are free from any technology nodes. There I'll search for VDC, for a DC voltage source, in order to get my supply voltage, and DC voltage value I'll mention as 3 volt. Click on hide, and I'll place it over here. And then input is going to be a pulse, continuous pulse signal. So I'll look at V pulse source. Voltage 1, I'll have it as 0 volt, which indicates logic 0. And voltage 2, I'll have 3 volt, which indicates logic 1. Period, I'll go for 20 nano. Delay time 10 nano. Rise time 1 pico, fall time 1 pico, just for example. Okay, nothing specific. And pulse width I'll take as 10 nanosecond, which is 50% of your period or a duty cycle. Place it over here. I need ground terminals for all the three. We'll go for add instance again and look for ground. And then click on hide and place it over like this. Okay. Now use wire to complete the connection. So you can use soft connection also. I'll let you know what is soft connection. Okay. So whatever you do here is called hard connection, connecting each and every terminal by wires manually. This is hard connection. Okay, soft connection, I'll let you know now. Okay, I just take the nets and I'll name them by using label. Okay, so for labeling, I'll use the short key L. Okay, uh, so I'll label it as VDD. So same thing as you name the uh, ports. Okay, you can name, you can give any number of names or any type of names, but separate them with spaces. Okay, and then input, which is going to be a gin. I'll take it as a underscore in, and then I need output of inverter, right? So I'll give as inv underscore out. Okay, click on hide and place them in the same order. I need a VDD over here and over here, AN over here and over here, and INV out, I need it over here. Hope this is fine. So once you have completed, you can go for check and save. In the command interpreter window, I don't see any errors or warnings. Everything is fine. Now I'll go for, I'll close this and create a config view. I'll close this. To create a config view, I can close this log file also. To create a config view, what I'll have to do is, from the library manager, I need to select the cell for which I need to create the config view. Select the view as schematic, go to file, new, and create a new cell view. The type has to be config. You can see config over here. So select config, click on OK. Go for use template in this new configuration tab or new configuration window. Go for use template, and under template name, select the simulator. So for mixed signal design, you have to make use of AMS simulator. But for other designs, you have to select Spectre. So you can see Spectre over here. This step is applicable only for mixed signal design. And for regular analog circuit design and simulation, you can just open your ADEL or ADXL or ADE Explorer, whatever it is, and you can start doing your simulation. I'll go for AMS, click on OK. Now under top cell in new configuration, you can see top cell. Under that, you can see view, right? So this has to be selected as schematic and click on OK. Now you can see table view, tree view. You can see the library, the cell that was imported from that particular library, and the view that is made use of. Under tree view also, you can see the same. So both are same, but different types of representation. You need to update this. So for updation, you have to go for view and select update. Click on OK. This is the cell, right? So click on OK to update it. Save this and click on open so that it should bring back your test circuit that you had created. Click on open. You can see the test circuit. So click on F to fit it to screen. Okay. Now go for launch. Select ADEL. Here you can see setup, right? Under setup, you can go for simulation or directory or host. The simulator has to be AMS. Okay. Select AMS as a simulator. Click on OK. Right. Again, go back to setup. Check for the model libraries. So this is what 180 nanometer is the technology node that you had selected, right? And under section, you can select the processing corners, which can be nominal, slow, slow, fast, fast, slow, fast, fast, etc. As of now, I'll go for nominal corner. Click on apply and select OK. Right? Now you can choose the analysis, type of analysis that you wish to work on. For that, I can go for analysis and select choose. You can see only 4 types of analysis are possible. As of now, it is okay if I just run a transient analysis for which the stop time is going to be 100 nano. Okay, Stop time is 100 nano, and I'll go for moderate type of accuracy default. Apply and OK. Once you choose the analysis, it comes under this analysis tab. Next, you need to select the signals that have to be plotted. So for that, I'll go for outputs. Under that, select setup. Under setup, I'll go for from design. Select the nets. I need to plot this input, output of this inverter, and the output of the buffer circuit. Three things I need to plot. I'll go back to setting outputs at the bottom and click on OK. I'll go back to ADEL, which is there at the bottom. You can run the simulation now. For that, you can go to simulation and select netlist and run, or you can select the netlist and run option over here. Click on that. Whatever happens, since it is a mixed signal design, first, and it also involves a HDL block. What happens is Verilog compiler, elaborator, and simulator. All three are invoked. Once this completed, let me show you. Yes, so we have got the output. Before that, let us go through the log file. You can see Cadence Design Systems. Okay, it is the files are getting converted into .vams extension. Verilog compiler is used to compile the functional block. Okay, and then elab and elaborator is used to extract the design, and then Spectre is used to run the simulation. Okay, the library files are checked out. NC simulator, NC sim is also getting invoked, and once it is done, it gives you the design. Okay, it starts running the simulation, and you can check out the waveforms. As of now, everything is merged with each other. You can go for graph and select split all strips to split out the input and output waveforms. First one is the input, where logic 0 is at 0 volt. To change the signal properties, I can select the signals, make a right click, and go for style. Select solid to get solid lines, and go for change width to change the thickness of the signals. Hope this is visible now. Okay. Now for input signal, you can see logic 0 is 0 volt and logic 1 is 3 volt. Output of the inverter, it is 1.8 volt. Okay, because you can just visualize a logic 0 or a logic 1, right? That is why you can see only 1.8 volt, and that too, this is the input of that CMOS. Okay, input of that CMOS inverter. Okay, and here you can see the output of your buffer circuit again at so it is not exactly zero. It is exactly zero, but you'll not. It's showing something like 61.3 millivolt. Okay, and here you can see 2.99, close to 3 volt. Okay, so hope it is clear till now. Mixed signal design and simulation. Any doubts till now? Any doubts, participants?
No, sir.
Okay, fine. Let us move further. This is about the mixed signal design flow until the simulation part. Okay. So let us go back to the presentation. Okay, let us start with SAR ADC, Successive Approximation Register Based Analog to Digital Converter. Okay, so what is a successive approximation register based ADC, where we are designing a data converter which converts the continuous analog waveform into discrete digital representation using a binary search algorithm. What is a binary search algorithm? It is a basic set, basic type of analysis, which is just you can imagine weighing balance, which you can see see in any vegetable vendor or fruit vendor shops, or when they come uh, at our doorstep on a tricycle. You can see a weighing balance, right? On one side they used to include the fruits or vegetables, and on the other side they used to add the weights. It is similar to that. That is a basic principle, which is called binary search algorithm. And this is a solution to mathematical puzzle which dates back to 1500s, 1500s. How to illustrate it? Let us assume that there is an unknown weight x, which we assume it to be 45 kgs, and the weights that are available for us are 1, 2, 4, 8, 16, and 32 kgs. This is the weighing balance that is available to us. On one side, we have the unknown weight, which is x, assumed to be 48 kgs, and on the other side, we don't have anything. What do we do first? We include the maximum weight, which is 32 kg. Now, compare these two things. Is 32 kg larger than 45? No, it is less than 45 kg, right? What happens? This is retained. And since it is not greater than 45 kg, the binary bit allocated to this is 1. Okay. Now, we include the next highest weight, which is 16 kg. Now, 32 plus 60, we get it as 48 kg, which is greater than 45. So we reject that 16 kg weight. Just imagine what happens if we include a 32 kg weight over here. This is still higher, right? This weighs more, right? So it keeps toppling here. If you include 32 along with 32 kg, include a 16 kg weight, what happens? This weighs more now, right? So it keeps toppling over here. Okay, but so to get the exact weight, you need to maintain this in balance. Correct. That is what we are trying to do. When we add 16 kg weight, since it is heavier than the unknown weight, we remove that. Okay, now 16 kg is rejected. The binary bit allocated for that is 0. The next highest weight available is an 8 kg. Now, instead of 16 kg, I include an 8 kg weight along with 32. So now 32 plus 8, we get 40. And it is less than the unknown weight. So the binary equivalent allocated for that is again 1. 32 plus 8, we include the next highest possible weight, which is 4 kg. 32 plus 8 plus 4 is again 44 kg, still not equivalent to the unknown weight. Okay, so we retain, we assign a binary bit 1 here. The next highest weight available is 2 kg. Now 32 plus 8 plus 4 plus 2 comes to 46 kg. Again, this side it becomes heavier. We are rejecting the 2 kg. Finally, we have the 1 kg weight, 32 plus 8 plus 4, 44, plus 1, we have 45. Now it is maintained in balance. The binary equivalent allocated to this is 1. Now we get the binary equivalent for 45 kg. And the 45 decimal number 101101 to the base of 2. This is the principle of a successive approximation register. We are just going to illustrate this as we move further. Based on this, how an analog to digital converter is designed. That's what we are going to see in our demo session. And this is going to be the functional block. We have a sample and hold circuit, comparator, a successive approximation register, digital to analog converter. We have a start converter signal and end of conversion signal along with a timing block. So apart from this, we'll be demonstrating all other things. We are still working on this block. Okay. Why do we need a sample and hold circuit in order to acquire the input voltage? A comparator is made use of to compare the input voltage to the output of a digital to analog converter, and this sends the data to successive approximation register. This successive approximation register gets an approximate digital code of the input voltage given by the comparator to the digital to analog converter. So what does the digital to analog converter does? It compares the voltage with the reference and supplies the and gives the output to the comparator. It acts like a feedback loop. Okay. So sample and hold circuit gets the input and sends it to the comparator. What does the comparator does? It compares the output of digital to analog converter and the sample and hold circuit, which gives the input voltage. The output is given to successive approximation register, which generates a digital data. This digital data is compared with the reference voltage at digital to analog converter, and it gives the difference to the comparator again. Okay, so this is the principle, whatever we have seen here. Okay, so these are the blocks involved, but how it works. The most significant bit of a successive approximation register is initialized to a digital one. Code is fed to digital to analog converter. It supplies the analog equivalent of the digital code to the comparator. If the voltage exceeds the input voltage, then the comparator causes the successive approximation register to reset the bit, or it is left as 1 and the next lower significant bit is reset to 1. Okay, this is what happens. Let me explain you once again. Initially, the most significant bit will be set to 1. This will go to the comparator. What does the comparator do? It compares this voltage with the input voltage. If it is less, then it retains the 1 and sets the next significant bit to 1. If not, it will reset the MSB to 0. Okay, and sets the next least significant bit to 1. This happens repeatedly. Okay, if it is a 4 bit, what happens is first 1 0, sorry, if it is a 4 bit, then the next significant bit also will be set to 1 if it is okay. Similarly here, what happens is if the comparator output is if the input is greater than the output of DAC, then this what happens is 0. The next MSB is also set to 0, and the next LSB is set to 1. Like this, it happens like this. Okay. Now, so this is what we are going to do is we are going to show the SAR ADC design using discrete ICs first on ORCAD PSpice. So what is the use of doing it in a doing it on a PSpice? It gives you an idea of how does a system look like, and whatever ICs that are available in the market. Like for example, you have an ADC 0808 IC. The output of that is compared to whatever is designed here, and you get an idea what to expect. That is why we are first designing it on ORCAD PSpice. Each and every block is designed separately, which makes every block will be designed separately and test it. Then we combine two blocks. Okay, any two blocks will be combined. Check for its output. Then another block will be included. Check for the output of all the three blocks. Then the final block will be included. So like this, we'll be going stage by stage. So for this block level design and verification flow, we'll start with the R2R ladder network first, and then we'll go for successive approximation register using D flops, and then we'll design the comparator, the sample and hold circuit. Timing control alone, we are still working on it. Then we'll have the system integration and the basic functional verification by simulation. We'll stop here, and we'll continue in the next session between 2 p.m. and 4 p.m. So any doubts till now? Any doubts, participants? Sir, is this okay? Shall we stop here and continue in the next session? Because we'll have the demonstration in the next session.
Okay, sir.
So
And no
next
time,
session is,
sir. The
yeah,
morning session get completed, sir.
yes. So the next session is between 2 p.m. and 4 p.m., right?
Yes, sir. 2 p.m. to 4 p.m.
Okay. So during that time, we'll go for the demonstration.
Okay, sir.
Okay. Yeah. Any doubts, participants? You can also give me the feedback either on chat box, or you can unmute yourselves and let me know the feedback about this first session. Feedback, participants, regarding this session. Online feedback you can take care, no issues, but I would like to hear directly from you.
Participants, your mic also enabled, or you can use the chat box.
So Lokesh Kumar Verma has told like it is an informative session. Thank you, Lokesh. Anybody else?
Participants, we will share all our recordings regarding this FTP at the end of this FTP. Thank you.
Demonstration is clear. Thank you, Azila. Knowledgeable session, informative session. Thank you all. Any negative feedbacks? Negative feedbacks are most welcome. Thank you, Kokila ma'am. Thank you.
So thank you, sir.
Yeah. Yes, sir. Thank you. Thank you very
Thank you,
much.
sir. We'll meet in the
We'll
afternoon
again.
session.
Yeah, sure. We'll all get back together by 2 p.m. Thank you all. Thanks for your
Thank you.
patience.
Dear participants, the day 6 session 1 attendance and the feedback link is posted in chat box. Kindly fill it soon. It will be open up to 30 minutes only. Thank you all. One kind information while filling the feedback form, kindly select your respective FTP ID. Thank you. Dear professors, the attendance and the feedback link for this session is posted in chat box. Kindly fill it soon. While filling the feedback form, kindly select your respective FTP ID. That FTP ID document is also shared in the chat box. Kindly notice that. Thank you all.